All right, so force is a push or a pull upon an object resulting from the object's interaction with another object. So forces are only going to exist as a result of some type of interaction. All right, and so yesterday we talked about all the different types of forces. We kind of categorized them into contact forces and action and distance forces. So we talked yesterday again about how contact forces are forces that result when two interacting objects are physically in contact with each other. So contact forces only work, or they work by two objects like actually touching, being in contact with each other, hence why they're called contact forces. Then we also have action at a distance forces. So those are forces that result even when two interacting objects are not physically in contact with one another, but they're still able to push or pull despite the physical separation. Right, so in that list from yesterday, we had like magnetism, electricity, and gravity. Right, all of those forces are still at work even if the two objects are not in contact with one another. Right. So the force of gravity from the earth is still pulling objects down even when the objects aren't like on the surface of the earth. It's still working.
I feel like, you know how like if you have like one of them really soft fuzzy things that's in your rubber don't work, and you like really touch it, and like before your hand touches it, you know how it shocks you sometimes? Is that force?
Yeah, so it's static electricity. It's your body, or like the object, it's really your body discharging onto the blanket.
What kind of force is it?
It's electric. It's an electrical force.
I wasn't sure because I know there's like friction.
Yeah, so it's basically when we're gonna get in depth into electricity here a little bit later, but there's an electric field that's at work there, and that's what allows the force to happen. Yeah. So.
I was just wondering.
Yeah, no, that's a good question.
Anytime like anybody talks about this stuff, I want it to have the feel of myself. You know what I'm saying?
So the unit of force is newtons, right? So when we talk about force, we're talking about newtons. So the symbol for that is just a capital N. Also, force is a vector quantity, which means it needs magnitude and direction. So now we're going to talk about Newton's first law of motion. So Newton's first law states an object at rest will stay at rest and an object in motion will stay in motion with the same speed and same direction unless it is acted upon by an unbalanced force.
I'm not going to write this down because it's already on my other notes. Or on my chapter notes.
Okay, that's fine.
Oh yeah, I forgot about that.
So basically what that comes down to is we've got balance. We're going to go into more detail about balanced and unbalanced forces. But balanced forces, what that means is your object is either going to be at rest, so the velocity is going to be 0, or it will be in motion, right, which means the velocity is not 0. However, for balanced forces, it means that the object is not accelerating, right? So it's either staying at rest or it's going at a constant speed in the same direction, is basically what Newton's first law says, until some other force acts upon it to like accelerate it in some way. All right, so Newton's first law is also known as the law of inertia. So inertia is the tendency of an object to resist a change in motion. A really good example of this is when you slam the brakes on your car, right? So do all of you drive? Right? So have you all had that moment in your driving life where you've had to like slam on your brakes really fast? Right? So what happens?
Everything goes forward.
Everything flies forward, like including you, right? That's why we have seat belts, right? So the car is moving, right? You stop the car, but your body is still technically moving with the car. But when your body's like flying forward like that, it's resisting that sudden change in motion, right? That's inertia. sounded painful.
That didn't feel good.
So, does that make sense to everybody? Kind of, sort of. Now we're going to talk about
Wait, go back real quick.
Now we're going to talk about balanced versus unbalanced forces. So, balanced forces are forces that are equal in magnitude but opposite in direction. So, balanced forces allow an object to maintain its state of motion, which means that it's not accelerating. So then unbalanced forces means that they're not equal and not necessarily opposite in direction. And when there are unbalanced forces acting on an object, that means that they cause an object to accelerate. In the direction of the net force. So, I basically drew picture examples of what balanced and unbalanced forces look like.
Do I need to draw them?
I would highly recommend it.
Okay.
So, for balanced forces, right? So we have an object, right? And so you can, again, they're equal but opposite. So you have, in the first picture I drew, I've got a 5 Newton force going to the right and a 5 Newton force going to the left. Right, so if those are the only two forces acting on an object, that means those forces are balanced because they cancel each other out. Right, and then it would also work if the forces were going up and down instead of left to right. And technically, you could also put all 4 of those 5 Newton forces on the same picture. As long as the up and down ones would cancel out and the left and right ones would cancel out. Then they would be considered balanced forces. Right, and then unbalanced forces are forces that are unbalanced, right? So you could have like 7 newtons going one way, 2 going the other. You could have them both going in the same direction. Right, you could have 2 that cancel out in one direction, but then have another force going, like the bottom one, you've got the 2 5 Newton forces that cancel each other out, but then you still have the 3 newtons up. Anything where in opposite directions they don't cancel out to 0 is considered unbalanced. We also have Newton's second law, which states that the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force. And it's inversely proportional to the mass of the object. So basically, it can all be summarized into the equation F net equals mass times acceleration.
Scary. I was like, is it gonna be like 29?
No, it's not. So for every action, there's an equal but opposite reaction. So forces are always going to come in pairs that are equal and opposite action-reaction force pairs. So a good example of this is like when you jump on a trampoline, right? So you exert a force downward onto the trampoline, and the trampoline exerts a force back up on you, which is what pushes you up into the air while you jump. And so as we continue on talking about forces and things, we'll get into more detail with these, like we'll combine them to other specific topics. But I just wanted to make sure we had kind of a broad understanding of Newton's laws before we got too far in. Tomorrow we're going to start doing some force practice with the Newton's second law, with the force equals mass times acceleration formula.